So Andrew, hopefully you're ready to go and you can kick my screen off.
Yeah, hopefully.
Hopefully, oh good, right. Hearing your voice is good, so that's a good start, yep. No, thanks. So Andrew's going to tell us about the evaporative drying of droplets project, and very great to have you here, Andrew. I mean, having had experience in the real world, so to speak, having been part of Procter & Gamble in your previous life, no doubt formulation, this is bringing things home to you. So hand over to you at the stage.
Thank you.
I'll try not to be too cruel on you on the time, but if you could stick to time, that would make my life easier. Thank you.
No problem. I will do my best. Well, thank you all for coming. So yeah, I'm Andrew Bailey. I'm in chemical engineering at University of Leeds, and this presentation is really going to focus on highlight a few aspects of the project, really how we go from droplets to particles, and highlight a few key results. So the project is done with Durham and Bristol universities with the groups of Jonathan Reed and Colin Bain. The main project is funded by the EPSRC, but I'm also going to show some results from the associated projects funded by various people. And we have a lot of industrial partners in the project, too numerous to mention, but thank you to all. And of course, all the work was done by various postdocs and students associated with the project and the associated project. So without much ado, because we are always short of time, what are we going to talk about? So we're going to talk about how droplets become particles, and the project focuses on both free particles, so particles in or free droplets in air, but also a little bit on surfaces. But we're going to focus on droplets in air. So we're going to look at a single droplet, how droplets interact, and then within the process, clearly we have billions of particles, how the process interacts with the particles a little bit. Also, all come to create that final formulated product. Might be a powder, as in a spray dryer, which you've got here. If people aren't familiar, that's a airflow in a spray dryer. Or it might be on a surface, if you're trying to make a coating on the surface. One thing to think about when we're drying single droplets is there's a lot of complicated physics going on when we dry a droplet. We have the conversion to a solid, so that the phase change, we have various concentration gradients that are established in the particle. So as a particle evaporates, the solids or the molecules in there which aren't evaporating, the solute can get concentrated, and typically does get concentrated at the surface, and that drives a lot of the behaviors we see. So we have concentration at the surface of a particle, and then also we have mechanical effects, and one of those which we looked at, and I'll highlight some of today, is what happens when we have a vapor bubble growing within a particle and puffing up a particle. And we mustn't forget droplet interactions. Here's oh no, it doesn't work if I do that. Interesting. Here we go. So here we have some particles or some droplets colliding, and you'll see actually they don't coalesce as you might expect, but they bounce apart in this particular setup we have here. And we'll highlight some of the work we've been doing in that area, as it's important to a number of processes. So starting off on the single droplets, we're going to look at crystallization. So this is work done in Bristol by Jonathan Reed's group. They have what's called an electrodynamic balance. This suspends a small droplet within an electric field. They shine a laser across it which scatters light, and they collect the signal from the light. And from that you can get very accurate size of the droplet. And so here's a couple of drying curves. So you've got one droplet, you expose it to some heat, or you can change the temperature or the RH clearly to change the drying, and you can create drying curves. And in a simple case here of water, you can get a drying curve, and that fits very nicely with theory. In fact, it's very, very accurate method of doing it for a nice single component system like that. Yes, in the current setup, got a this kind of type of temperature range, and you can clearly change the humidity. So what happens if we put something simple in there like sodium chloride? And first of all, just to say a little bit about the signal you get. So this is the scattering signal you get, and you can model with something called me theory to and back calculate the droplet size. And that works well if you've got a nice single component droplet. But what Jonathan's group has been doing recently is looking at what signals you get for different types of droplets. So core shell droplets, included droplets. Actually, if you go to a particle, so you lose, you generate some opacity and you lose the sphericity, then we lose the ability to get a size, and we get this type of signal here. And what we can do is use that to find out when we're getting crystallization within a drying drop of crystals. So here are some drying curves for sodium chloride. So the sodium chloride, there are 233 drying curves, in fact, overlaid. You can see very reproducible, a predictable drying curve before we get crystallization. So at this point where you start getting the clouds of particles, this is where you're getting crystallization. And for sodium chloride, we find this is very reproducible. And the time to get that initial crystallization within the droplet is very sharp, reproducible. And actually, if you do some modeling to understand the concentration gradients within the droplet, what you find is that that crystallization always occurs. It's occurring actually at the surface of the particle when the surface of the particle reaches a certain supersaturation, and that remains constant across a reasonable range of drying conditions. So sodium chloride, we get this predictable, repeatable effect. But if we have a look at a different salt, again, a very simple salt, sodium nitrate, again, we got a drying curve, but this time we see some of the particles we seem to be able to track for a long time through their drying through time. And so these particles, they're not crystallizing, they're remaining amorphous with time, even though they're dried down to essentially their equilibrium moisture content. And you can see the efflorescence time, which is what the aerosol guys call crystallization, I should emphasize. So this is where crystallization happens, and you see you've got a broader curve, and sometimes it extends out of here. So you can, if you look how that changes with well, that's time. I'm going to just skip past that. You can get a probability distribution curve out of that. But if we look how that changes with the supersaturation or the drying rate, so if we increase the humidity, we decrease the drying rate, and essentially we're changing the equilibrium supersaturation. And you can see that at the lowest humidity, the highest drying rate with the highest supersaturation, I think these are mean supersaturations, then we get 100% crystallization. But as we decrease the drying rate, we are decreasing the supersaturation, and we get less and less crystallization. And you can see that in these distributions here of the time to crystallize as well. So that's one. That's looking at crystallization on the small scale. We can also, Jonathan's got a rig where he can create these small droplets in a very controlled environment, and we can have a look at what happens to the morphology of the particles in these systems. And so for certain circumstances, these are about 10 microns, probably about 50 micron initial drop size. If growth dominates, you get these little square crystals with a dimple in the middle. And as you change up the drying rate, you can then look at what type of crystals you get in these systems, and you move from the slower drying rate, so higher RH, you get more and more nucleation versus growth, and you move to hollow multi crystallite particles, and you often see a little hole in them as well, where perhaps some water is needed to come out, or some vapor is needed to come out. Now, if we compare that with what you get on a spray dryer, so that was on a little droplet chain, so we're creating very repeatable particles, giving them a repeatable, roughly uniform drying history. If we compare that to what we get from a spray dryer, then you can see, well, we got some interesting looking particles here. And so these were made from a higher concentration solution and a little bit of a higher temperature. So we're driving up the temperature and the concentration. So one of the limitations of the smaller devices is we need to start with very low concentration. So all those droplets you saw, those particles you saw earlier, were from low concentrations. So if we increase that concentration, we're increasing the supersaturation, and we get these very interesting shapes of particles. In fact, we can drive square cross-section particles from a spherical droplet. And sodium chloride's got a cubic crystal structure, and we think that these are essentially three-dimensional hopper-type crystals, which you see when you have high supersaturations. So I think we're getting there's an interaction with the crystallization and with the shape of the droplet, and the fact that you have higher concentrations at the edge is driving these crystalline shapes, and leading to these unusual structures. I should say we're doing some more work to try and understand what exactly is driving these. We can also look to see what happens when you put additives in these systems. So this is sodium chloride with maltodextrin. So the maltodextrin concentrates at the surface and changes the crystallization behavior at the surface because it's a higher molecular weight than the sodium chloride, and you get these pretty little what they call fleur de sel crystals, which are driven by diffusion limitation at the surface. So the maltodextrin is changing the diffusion at the surface, and we are getting different crystallite structure at the surface. And inside these little crystals, well, you've got diffusion at the surface. We're getting more typical cubic sodium chloride crystals. So you've got this shell structure with the fleur de sel, and then inside you have crystallization into a more typical sodium chloride. Now, I was saying that we struggle with the concentrations on the small rig Jonathan has, but we also have a filament rig in Leeds where we can suspend a droplet on a filament. We can stick a thermocouple in. We can actually weigh the droplet if we want to as well, and we can video it and see what's going on. So if we have a look at what's going on in some sodium chloride, I think there's sodium chloride here. Actually, because we have this filament in, we actually have introduced a site for nucleation, and we do see nucleation close to this. This is a thermocouple bulb, the dark area in a sodium chloride droplet. We do see nucleation there, but then the nuclei fall off and they actually fall to the bottom. And there's some growth going on as well. And what we actually see here, that we have some heterogeneous nucleation, we have some gravity, and then actually capillary forces arrange the particles at the bottom. So if we have these droplets, I should say, are order of a millimeter, then we get collection of the particles at the bottom, and the capillary forces organizing those particles in stacking them up in the case of sodium chloride. And we can actually look at and see what's going on here. So we have these, we have gravity is having an effect, increasing the concentration here, but we can see growth. And if you look in a couple of these things, you can see these fleur de sel particles just growing here on the edge of the crystal. The reason we have, excuse me, the crystallization here is just the direction of the airflow going across the crystal. So that was just to give you a few insights into what we can do and what we've been looking at in terms of crystallization, trying to understand that, and still many challenges, but you're beginning to see some of the fascinating structures you can get when you dry these droplets, and how we can use these single methods to control the droplet experience and look at what's going on in terms of crystallization. So now we're going to move to drying at high temperatures. And when you dry at high temperatures, what's different? Well, high temperatures, we can have boiling. And And when you have boiling, clearly you're going to get vapor bubbles, and the vapor bubbles are going to change the structure of your particles. The reason you get boiling, you wouldn't get boiling in a pure solvent droplet, but if you have some solute in there which is slowing down the transport of water to the surface, what we call the evaporative cooling that's going on in a droplet. If you've got a lot of free solvent, evaporative cooling will keep the droplet temperature lower. Well, that becomes less as you stop the transport of liquid to the surface. So when we get boiling, we've always got some kind of solute or some structure which is stopping us, stopping or slowing down drying. This project we were looking at to try and understand that more and map out the behavior. So just to give you a couple of insights here. So here's a sucrose droplet actually drying on the filament, and here is the drying curve. The blue line is diameter and the red line is temperature. Now if we watch over here, just up here, you've got a bubble forming. So it's getting to boiling point, and there we go. What's going on there is rapid boiling events, and eventually, in this case of sucrose, it gradually calms itself down, and you can see in this blue line, which is the diameter, this was where it was just shrinking as it was drying, and then it reaches the boiling point here, just a little bit above 100 degrees C, and this is where it's boiling. So all these blue peaks here are what you just saw on the left with the rapidly changing droplet, and then gradually it's come down and then dried as a single droplet. So what's happened there is the material properties of sucrose have remained relatively liquid-like, shall we say, at these moisture contents. So even though the drying has slowed down within the droplet, the material properties are more liquid-like, more viscous behavior, and that's resulted in seeing no kind of evidence of the puffing in the final droplet. If we look at silicate, then here's some diameter versus time plots for silicate for different concentrations, and you can see, well, at this concentration, which started at 45%, we're getting very, very large particles. But what you also notice is that the particles no longer shrink into down into that final droplet size, which you might expect to be around here. They maintain their size. So what's happening there is that the physical properties of the silicate are sufficiently solid-like once it's puffed that they maintain the droplet size. And in fact, we can relate relate the behaviors we see through to what we're seeing in terms of the material properties of the system. We've also looked at HPMC, which again is very interesting because this has a gel formation. I don't have time to show you that now. What I'd like to show you now is just give you an insight into, hopefully if I press this, yeah, we go, an insight, if we're looking on this left screen, into what's happening when they puff. So this is actually a blown up balloon of sucrose, and that is the film rupturing. And then we get this little jet of liquid which comes out of the particle, of the droplet. And gradually then this will re-inflate. And again, it will burst. Sometimes they spit out this little, what you might call a Worthington jet, which is where you have a film which contracts rapidly and forms this reflexive jet. And that's why you get, these are the liquid-like properties that were giving you this behavior. If we look at, in contrast to silicate, so this, if you remember, here it's ruptured over here. We've given some dynamics to the filament it's on, and then you see this crumpling. So a lot slower than here. We have a crumpling behavior as it's deflated. And then if I showed you longer in the video, you would actually see this eventually reflate. So this little particle reflates, and it can go on. Here we go. It's going to start to reflate now, and do this several times. Typically on the final one, it doesn't quite burst, and it maintains then this structure, and has a final larger puff diameter. Okay, I think I'm going to run out of time very rapidly. So we've looked at modeling some of these systems. We working on coupling droplet motion with the drying, and looking at colloidal systems too. And there's lots of interesting things in colloidal systems, and that's kind of work in progress, where Jonathan's looking at some really using the EDB and the single droplet rig to look at colloidal systems. On surfaces, actually, this work's done in Durham, and they're looking at, when you dry an emulsion, can you create capsules? And by essentially playing with the phase diagram in the system you've got with a number of solvents, you can create little capsules in situ. So he actually creates the emulsion in situ in the nozzle, controlled size, and then he can when they dry down, the emulsion solidifies into little capsules on the surface. It's just a highlight. We're not just doing free space. We're also doing things on surfaces. Collisions. So this is a spray dryer. There's lots of collisions which lead to different types of agglomeration in a spray dryer. And what we've done here is look at the maps that you get of the different behaviors you get. So you get bouncing behaviors, you get coalescence behaviors as you increase the essentially the Weber number. Think of that as the velocity, and then V is the offset, and you get these different behaviors that you can classify. So this is stretching separation up here, and reflexive separation at the bottom. And there's reasonable amount of literature out for this, but what we wanted to do was extend some of that literature up into higher viscosities, and to look at different sizes of particles as well, because people tend to do the ones that are easy to do experiments on. And so we built this little rig with the help of various people, where we can collide the droplets and look at their behavior. So we use piezoelectric nozzles, and we video them, and we have a strobe where we can make sure they're aligned in the other orthogonally, as it were, and then we can create these maps. So what we've chosen is to do. We chose HPMC as the system to increase the viscosity, so we can increase the viscosity about 10-fold, and then we've looked at not only droplets with the same viscosity, but what happens in spray dryers clearly is you have particles with different moisture contents. We wanted to look at, well, what happens when you collide droplets with different viscosities. And what you'll see, they all look roughly the same. You find this reflexive separation region disappears as you increase the viscosity, and some of these boundaries change. So we've looked at and built models for how some of these boundaries change with viscosity, and looked at improving the models that are out in the literature. When it comes to non-identical viscosities, or viscosity, just first to say then, in bouncing, as you increase the viscosity, you're actually more likely to get coalescence, because the air layer which causes bouncing, there's an air layer trap between the particles, is less likely to form when you have a higher viscosity droplet. And then when you have different viscosities, well, you get the change between coalescence and bouncing, different Weber numbers, which is intermediate to the two viscosities. But you also start to see different effects, because what happens is the time scale of the bouncing behavior creates asymmetry, and the asymmetry then leads to different effects. In this one, you get this little kind of partial coalescence kissing effect that you would never see in a symmetric type system. I'm going to skip through this relatively fast and just highlight here what happens when you have asymmetry, when you have this so-called stretching separation. So when you have a more of a glancing collision, you get the stretching separation. You have a large ligament form, which can form into lots of little satellite droplets. What happens when you have dissimilar viscosities is the dark one is the high viscosity and the light one is the low viscosity. Then the ligament is always formed, as one might expect, from the lower viscosity, and therefore the separation boundary that we see in those maps is more linked to the lower viscosity particle or droplet. I'm going to, in the interest of time, because I'll probably be told to be quiet a little bit in a little bit, skip past some of these.
We've got sort of 2 minutes left, I guess.
Yeah. We've looked at different viscosities, different sizes, and get some different effects when you see that, and that just summarizes some of these changes we see. But I wanted to just touch on a little bit of modeling to finish off. We've looked at different ways of looking at contact dynamics where we're drying at the same time. But in terms of modeling, just to finish off with some modeling, this was some work which started with the Adopt project, where we modeled a spray dryer and improved the airflow. But if we want to model drying in a spray dryer, we need to couple in the dynamics of the droplets, and we need to couple in what's going on within the droplets. And we can model here some trajectories of particles in a spray dryer. So their droplets are formed, they swirl around, they come out the bottom. Their behavior changes with size. But most of the time, historically, people in these models, because of computational limitations and expense, simplified droplet models have been used. And one of the challenges with doing that is you lose some of the information about structure and the influence of particle drying history on structure. And so we put them in a more complicated model, this so-called diffusive model, diffusive transport model. And these are some, and when we look at the temperature profile, we don't see much difference in that, just to compare with the simplified model. But then we look at in a little bit more detail, and what we find is that, so that if you like, the DT is probably the best model, but it's expensive to run. So can we get decent results with simplified models? Well, the CDC1 and the REA are the more simplified model. You see the yield, for example, so this is the amount of powder coming out of the spray dryer, is pretty low in these systems, because the drying is not quite captured and the the surface properties aren't quite captured in these models. If we make some changes to the CDC model by making it more responsive, we can get improvements in the CDC2, but we've gone, if anything, slightly the other side. So work in progress will be to get simplified models which are closer to this diffusive transport model. So I will leave that there. I don't know if there's time for questions, but thank you for listening.
Andrew, thank you very much. That was a great tour de force on quite a project of work. I'm afraid we haven't really got time for questions, unfortunately. People are picking them up in the chat. There are a few there. It'd be great if you can answer them.
Sure.
As I said, if people can identify who they're answering to and how they're asking of, that would be brilliant. So thank you very much, everybody. Thank you for that, Andrew. And